answer the question. It's a good question. When can you use KB? Primarily use KB for when you have weak base plus water. If you have weak acid and conjugate base, I recommend using the Henderson-Hesselbach equation, or you can set up a nice table with Ka. And if you want to give it a try, you can set it up with KB as well. But you have to write the equation for the ice table, correctly for the type of K value that's used. So, and to keep it simple, just always work with the Ka, okay, in that case. So when you have weak acid and conjugate base both present, you'll get the answer. Because the way that the small x approximation works out, it'll work out for you. Okay. So hopefully that explains that. Anything else that you want to go over on that? Now let's go a different type of problem. Now, go back to this part B. We mix this and prepare the solution, mixing 100 milliliters of 0.25 molar ammonia with 100 milliliters of nitric acid. So again, now you ask yourself, what do you have here? Okay, and you have now a weak base right there, ammonia, and nitric acid, strong acid. So the nitric acid, HNO3, that's basically what you have. You don't care about that nitrate ion. It's not going to do anything. It's a spectator ion. But this nitric acid dissociates completely to hydronium ion and the nitrate ion. Okay? 0.2 molar nitric acid is really 0.2 molar hydronium ion. Okay? And that's going to react with ammonia. Okay? So, let me get to part B here now. So you can see that's the first thing I did, identify weak base and strong acid. So strong, I do stoichiometry of moles. So what's the reaction taking place? This is what you have to figure out. It's the ammonia, the weak base, plus that strong acid from the hydronium ion coming from nitric acid. What's it going to form? Forms the ammonium ion in water. Here you transfer of H+. Goes from the acid to the base. Okay, so you transfer over hydrogen, and you transfer over a positive charge. Okay, now you have the reaction in mind. Okay, you have the volumes and you have the molarities. You calculate the moles, because that's what you do for stoichiometry. So we end up with 0.02 moles of ammonia and 0.02 moles of hydronium ion. And again, I'll put this on Blackboard afterwards. So I calculate the moles of each. Notice in this particular problem, I had to indicate the amounts of each because I needed the moles. Okay, so now, just looking at it, and it's a one-to-one reaction, I see that there's more moles of ammonia than I have of hydronium ion. So, the limiting reactant in this case will be the hydronium ion. So all of the hydronium ion reacts away, okay, forming the ammonium ion. And so the excess will be the ammonia. And what would they be excess in terms of moles? It's the initial moles of 0.025 of ammonia minus the amount that it reacted with the hydronium ion, which is equal to the moles of hydronium ion, which gives you the moles of the ammonia that's left over, 0.005 moles. Okay. So, at this point, and from stoichiometry point of view, basically the hydronium ion is approximately 0. It's not exactly 0. Okay, it's always some kind of equilibrium, but at this stage, we could treat it as essentially close to 0. So the amount of ammonium ion, of course, is the amount of the moles of hydronium ion we had initially, okay, because all the hydronium ion reacted to form the ammonium ion. All the, hydronium ion reacted to form the ammonium ion, right? So all the H3O plus reacted with the ammonia to form the ammonium NH4 plus. And you have 0.02 moles of that. So after the stoichiometry, what do you have left in solution? You have 0.02 moles of ammonium ion, and you have 0.005 moles of ammonia. So you have your weak acid, the ammonium ion, and the conjugate base, ammonia, and hence that's a buffer solution. And you could have, since you have both of them, use the Henderson-Hesselbach equation. And what's nice about the Henderson-Hasselbalch equation at this point is that you have the moles of each. Okay? And the Henderson-Hasselbalch equation, you don't have to go back to molarities here, because that ratio could be in moles instead of molarities. So that's the added advantage of the Henderson-Hasselbalch equation. Okay? Okay, so now you do part 2 of the calculation. So part 1 was the stoichiometry. So which we end up with so many moles of each of the two. Okay, and 0.005 ammonia, Greek base, 0.02 moles of ammoniumine, Greek acid. So now we do this equilibrium for part 2. We better define more precisely what we have in terms of concentration of these species. Okay, and since it is the conjugate acid, weak acid and conjugate base, use the Henderson-Hasselbalch equation, it's fine. So pKa was already predefined as 9.25. Is there a question out there? I heard someone talking, so. Oh, no question? Okay. And then you have log of the ratio. So that ratio could be just moles. So notice the ratio here is the 0.005 moles of ammonia divided by 0.02 moles of the ammoniumine. So in other words, that ratio in that log term is nothing more than the moles that you got from the stoichiometry of the limiting reactant stoichiometry problem of hydroniumine reacting with the ammonia. Okay, acid reacts with base. And it's a strong acid, so it goes to essentially completion. And I said essentially completion, not exactly completion. And so that's what brings about the second part of the calculation, where we have to fine-tune the results when we do the equilibrium calculation. And since we have moles already, using the Henderson-Hasselbalch equation is best. And that, it's basically using pKa. Okay, so you do the calculation, it's pH of 8.65. Okay? Because the log term here, notice you have more moles of acid. Whoops, I can't see that. 0.02 moles of acid versus 0.005 moles of base. So you have more acid than base. Notice that the log term became negative, and so your pH is below pKa because you have more acid in that solution, weak acid, than you do weak base. And so that log term is negative, so it brings the pH down from pKa, and it goes to be somewhat less than pKa, meaning more acidic. Okay? Okay. So this one I did the other way as well. The ice table. So instead of the Henderson-Hasselbalch equation, it could be done with an ice table. Okay? But to do that, you have to calculate your initial concentrations. You take the moles that you calculate by stoichiometry, 0.005, 0.020. Okay, divide by the total volume of solution, not individual volume. Our total volume is 200 milliliters because you mix 100 milliliters of one thing with 100 milliliters of another thing. Gives you 200 milliliters of solution. So you divide by the total volume, and you get the molarities, because with ice tables, you have to use molarities. Okay, set up the ice table, and you have the weak acid and conjugate base. And I think the question that was being referred to, should you sub for Ka or Kb? And mathematically, for the ranges of types of compounds we do, we're going to always, just using Ka is fine. And always assuming that it goes towards Ka direction is fine. Okay, because in the end, we're going to use a small x approximation to get rid of it anyway. Okay? And so whether x is positive or negative, it's really not going to matter. You could determine it based on doing a reaction quotient, but in the end, it's not going to matter. Because why? Because basically, we're going to do the small x approximation anyway. Okay? Small x approximation, basically, we're ignoring the x's here, assuming they're small compared to the initial concentration. When can we do that? Well, look for that when the K is very small. 10 minus 10 is a pretty small number. It's orders of magnitude smaller than the initial concentrations of 0.02 or 0.1. Okay, so when K is very, very small, much smaller than initial concentration, you can use the small x approximation. Okay? So when you do that, you have a much simpler problem.